Hello, it's Toby, and welcome back to the series where we walk through the LLVM tutorial. The tutorial is called My First Programming Language Front End with LLVM, I believe, and we're making a programming language called Kaleidoscope right there. And we're in the middle of, we're at the latter half of chapter 5. And in the previous episode, we wrote the parser for the for loop syntax. Now we're gonna write the generator, the LLVM IR code generator for the for loop construct. So let's go do that. Let's walk through this LLVM code here. LLVM is its own language, is something I want to mention, and its code looks like this. And let's look through this code for the parts of it that the for loop is going to generate. So these labels are like go-to labels. You might be familiar with labels with while loops, I believe, in C and a lot of other C-derived languages. Your while loop statements can actually jump to labels. So this is the entry point label. Later on, some code, I don't think anything jumps to the entry point actually. It is the entry point. Here we're gonna branch to the loop label, which is right here on the next line. So this is not totally necessary, but this is just the construct, the standard construct that is a convention that we follow, I guess. I also believe LLVM has a scheme where like they have to craft a flow graph a certain way, and maybe this is necessary to start off the flow graph with a jump statement. I'm not sure. Later on, you're going to jump back to the top of the loop via this BR statement. BR means branch, is a shorthand for branch. So when you use the branch statement, you can use a conditional, which in this case it is using, but you can also optionally just always branch to a label. So there's two variants of the branch instruction: always jump to a label, or jump based on this conditional, whether you jump to this label versus this label. After loop is right here. So this is saying if the loop condition is false, we're gonna jump out of the loop and move on and start the execution at after label. This looks very suspiciously like the loop counter. Yeah, I'm gonna double check to make sure I'm using the correct mic for the recording. Excuse me. Yes, I am using the correct mic. Alright. Alright, so let's see what's going on here. So this is loop counter. This phi is something I'm gonna try my best to explain. The phi is basically, it's gonna merge. Basically, it's gonna assign to I either this or, well, either not that, either this or this, based on from where the execution entered this loop label. And as you can see, and I guess that's why this entry label is needed actually, because in one case we encountered this branch statement which goes into the loop label, and in this case the entry point was entry, or in this case, I should say the incoming code was from the entry label, whereas in a different case, we had a branch statement here that jumped to loop, and for that case, the incoming code was actually from the loop label. So basically what this phi statement says is, if we came into here via the entry label, then assign the number 1 to I. But if we came into here via here, then assign next var to I, which I guess that was defined over here. So that's what that's saying. That's the phi construct, or the phi instruction. I did explain it, I believe, in a previous episode in this series. So if you're confused by that, go watch that episode. Although I don't remember which one that was. I'm sorry. I think I think I had a video that's specifically called the phi function or something. So look for that one. Anyway, and then we have this put char, which is just the code in the for loop. I think the code is this. This is the code. So that's the put char d. And then we're going to add 1 using the fadd instruction to I. I guess that's just the step amount of 1. Next var eventually comes back here and goes back into I. Yeah, this is kind of a weird thing. The variables in LLVM are constants. However, in this case, it's almost like for each iteration of this loop label, we get to assign new constants, right? So the I is like a fresh I for each time this loop label executes, and each time the I gets either this 1 if we came in from here, or whatever is the next var in the previous iteration of this loop. And the next var is determined here. It's based on I plus 1 in the previous iteration. So the next var in the previous execution of this loop goes into I in this execution of this loop, and then we move on and so forth. So this is the LLVM code. This is the termination test. Let me also talk about that. So this is saying fcom is a floating point number comparison. Floating point number comparison, this is double. That's just the type of the floating point number. We're comparing I versus n. N was passed in as a parameter, so whatever that is. And then, I didn't see the Kaleidoscope code for print star, but whatever. ULT, I think that means unsigned. Hello? My pen is behaving weird. Unsigned less than. I believe that's what that means. Unsigned less than. And then here is unsigned integer to floating point. We're gonna convert, because all numbers in this language are doubles. If we end up with an integer, we're gonna convert it into a double. And for all comparison operations, I believe the output is always an integer. So this guy is an integer 1 actually. I1 means a 1 byte integer, which means a 1 byte integer is either a 0 or 1. That's the only thing that this guy can be. So we're going to convert that 1 byte integer to a double, so it will be a number in double of either 0, it'll be 0.0 or 1.0 basically. And then we're going to do fcom again to compare. We're comparing one. One means not equal. O, I forget what O means, but this one actually means O not equal. There's a menu in LLVM that lists all these stuff. Let me see if I can bring it up. LLVM reference menu or something like that. I've used this. Yeah, there we go. And I'm gonna search for fcomp probably. Let's try this. If it loads, we will try it. Fcomp. There. So it has a list of all the instructions in the LLVM language. And it should tell us, come on. Dude. It's still trying really hard to load the page, I believe. There's also documentation for the 5 function, by the way, if you're interested in knowing more about any instruction. So there's this mode, basically, parameter, which you see here. So ULT is one of them. ULT means oh, I was wrong. I said unsigned, but it's actually unordered. It's unordered or less than. Unordered or less than? I don't understand, actually. What unordered? Unordered means either operand may be a nan. Oh, okay. So if either operand is not a number, then it returns true. I think that's what that means. Whereas ordered means neither operand is nan. So if O is the first parameter, if that means if either one is a nan, it's true. Whereas unordered means if either one is a nan, it's the first one. The first one means if either one is a nan, it's false. Actually, unordered means if either one is a nan, it's false. Unordered means if either one is nan, it's true. I don't understand why they chose to use unordered in this case and ordered in this case. But okay. All right. There must be a reason to it, I'm sure. But anyway, then we're comparing this number, which is either 1 and 0, to 0. So if it is 0, then we're doing this branch to test for this zero-ness. So if it is 0, then we're going to jump back to the top of the loop. Otherwise, we're going to jump to after the loop. Yeah, I think that's what's going on. This comparison will tell us whether it is less than that number. Yeah. And then that'll give us a true or false, which is represented with 1 or 0. And then we're casting it to a double. So it's this bool temp is 0 or 1, and then we're saying if it's 0, 0 would mean it is not less than n. And 1, and then we're comparing it to 0. 0 would mean it's not less than whatever this n is. And if it's not less than n, then that means it's probably n or greater than n. Then we want to jump out of the loop. So that's why we're comparing it to 0. Okay. Anyway, that's the explanation of that code, and that's what the code we're going to implement is going to spit out, more or less. Although it's not going to spit it out into this textual form. It's going to spit it out using this AST builder, which you will see very soon. So I'm going to follow this tutorial now and implement this Codegen method for the for Expr AST class. So I'm gonna copy this code here. Let me move this a little bit over. Okay, so we're dealing with a lot of stuff here. The for statement has these bits, and we're gonna start with generating the code for this bit. This bit is probably just a 0, a constant, but we're gonna need to codegen that. And we're gonna check whether that codegen succeeded. To give you an idea of what that did, that is probably the code that generated this literal here, is my guess. Yeah. Okay. Next. Do I need this semicolon here? Maybe not. Okay, next we're gonna actually make a new basic block for the loop header, inserting after current block. Let me start typing, and then I will try to understand what it's actually doing. Oops. Okay, so we're gonna get insert block and get parent. I think that is saying I'm going to get the current place within which I am, which is probably within a function scope or something. If this were the code, probably within a function, or yeah, it would be within a function where the for loop statement is used. So that's what the function is. And then we're gonna get a pre-header BB, a basic block. I think this is the one of the blocks, either the entry point block, either this block or this loop block. That's what a block means. But I'm not sure which one, the pre-header BB. Probably the entry point block is my guess. Oh yeah, I think this is the entry block and this is the loop block. Although for some weird reason, we are using different mechanisms for creating them, for creating each one. Okay, so this is, I believe this is saying we're gonna create a basic block called a loop inside this context. I don't remember where this context came from. And then we're gonna insert it into the function, like the function within which we are at this point. And then we're gonna go builder that create breakpoint, not breakpoint, create branch. BR stands for branch. So that's gonna create this branch statement here for us. Get insert block. This get insert block probably already inserted this block here, and then and then this is saying, hey, and then that puts the current context at this entry point block, and then this is saying add another block within the function, but don't insert it right here. And then we're gonna add a break, not break. I keep seeing BR and I call it break. Add a branch statement that goes to this loop block, and now we're gonna set insertion point at the loop block. BB stands for basic block, I believe. When you set insertion point, what that means is the next statement generating functions would go inside of that block. Which is what the next command does. We're gonna create a phi node. Okay, then okay, what is this doing? We're gonna create this phi node, which is that guy. We're creating this statement, essentially, is what this is doing. There's gonna be a variable. This variable is gonna be I, and that is gonna come from the var name that we have access to, because var name is a variable, instance variable within the for Expr AST class. So that's where we're getting var name. We're going to create a phi whose type is double. That makes sense because the type of our I, or whatever variable name that happens to be, is a double. And in Kaleidoscope, in the Kaleidoscope programming language, the only data type is double. So that makes that a no-brainer. 2, what the heck does 2 mean? I think that 2 might mean there's 2 possible places, two entries here, 2 incoming pointers for this phi node. That's probably what it means. That's my guess. I'm sticking to it unless somebody tells me otherwise. And then we're gonna add some incoming links. So the first incoming is the start val. Start val is this. It would have been in a 0 in this example. So start val would be this 1 over here. Start val is whatever our start Codegen generated. That's the start val. So this is saying it's generating this part of the statement. It's saying if you're coming from the entry point, which I kind of want to rename this guy to entry BB. Let me go ahead and do that. Okay, so if you're coming from the entry point, then the variable gets the value of start val, which would have been 1 in this case. And we're gonna probably do a second at incoming a little bit later on. Okay. And next, we're gonna do this stuff. We have named values. I don't remember these things. Within the loop, the variable is defined equal to the phi node, right? If it shadows an existing variable, we have to restore it, so save it now. Oh, okay. Where do we keep? This is a global variable. Holy crap. Oh. Wow. Oh, the variable Expr AST looks up the named values. Okay. To resolve variable references, and if it's not in there, then it's an unknown variable name, and I would expect like a variable assignment to write to this name values. A function. Oh, we don't have variable assignments. That's right, but we do have function declarations. Wait. Oh, not function the function parameter list. The function parameter list go into this named values. Okay, got it. Okay. I think I vaguely understand why we're doing that. And then we're gonna generate the body, and the body is that, basically. We're gonna generate code for the body, and then we're gonna do if there's a step definition, which is that guy, we're gonna code gen for that. But if there isn't, we're gonna default it to a 1. That's what we're doing there. So let's go ahead and do that. So if step exists, we're gonna set step value to the result of code genning the step. Okay, if even after the code gen we didn't get a step val, then there's a problem. We're gonna return null pointer to signal that it was not good. Okay. If there was no step definition in the first place, we're gonna make the default step value 1. And I guess that's how you do that. Next. This is an add instruction. We're gonna create a next var variable and create a add instruction which adds the step value to variable, which is our loop counter. Where was that defined? Over here. Yeah, it's the result of this phi node. We're adding the step value to it and assigning it to a new variable called next var, and now we have that. Then we have a loop terminating condition. This is called the end cond. We're gonna generate the code for the end condition, which is usually something like I less than n or something like that. Okay, we generate the end condition. We're gonna create a comparison fcomp1 fcomp ONE, which means not equal. We're gonna set it to not equal to 0, basically. So end condition is, I'm gonna use the AST builder to create a fcomp ONE, which stands for ordered not equal. Okay. Loop cond I think is the variable that received the output of this comparison. Yeah, that's that guy, and then we're gonna need another branch statement after that, I believe. But in order to set up the branch statement, we're gonna need to create this after loop basic block. BB. So that's here. Please excuse the noise if you hear that outside. Okay, I'm gonna create a loop ending block. Okay, so we create another block using this same pattern here. We first are inserting a new block that's called the loop end BB. Oh, wait a minute. What does loop end BB represent is something that I'm slightly confused about. This is saying we're going to create a conditional branch that's based on the end condition. It's either going to jump to loop BB or after BB. After BB is this after loop block here. Loop BB is that. But what is loop end BB? What is loop end BB is the thing that I don't totally understand. Maybe just another pointer to the loop block. Anyway, I'm going to go with that. Okay. And then, yeah, as I said before, we need to add another incoming to the variable for that phi node. Oh, I see. Yes, I believe this is the case. So loop end BB is referenced by this incoming, which is saying that's what we're doing is setting up this entry here. So this is saying if, excuse me, gonna ignore this phone call here. I'm sorry about that. It's basically setting up this entry and saying that for the phi node, if the incoming is the loop block, then I want the next var, the value of the next var variable, and the loop end BB is basically a reference, another reference to the ending, the loop block, the loop BB. But I think probably because this loop BB hasn't been inserted yet, it's just been created. You don't get an insertion until you call get insert block or something like that, I believe. So you create this loop block somewhere in midair, but you haven't inserted it yet. But we set insertion point to it so you can insert stuff into it, but the loop BB still hasn't been attached until you do this, maybe? No. I guess this is like we had the insertion point in the loop block here. Yeah, I think this is the get insert block is same as this guy, but get insert block is wherever your insertion point is, get the block where it was, whatever that is. And in this case, our insertion point was already inside the loop block. So this is used to reference the loop block in this incoming statement. I wonder if it would have worked if we simply change it to put this loop BB in here. That probably would have worked just as well. I could test that theory, maybe. But let me get it working the way that it's prescribed first. We're almost to the end of this chapter. Hang tight. Okay, so this is, it's putting back the named values of the old value, whatever that was, in case we're shadowing, like if I was like a passed-in parameter of a function or something like that, I believe. Okay, I think this is all the code. Let me try to compile this code and hope it works. Of course, it's not going to. Use of undeclared identifier constant FPF. I probably messed that up. It's constant FP, not constant. 456 constant FP. I think that worked, so I'm gonna try to run mylang.bin and try to write a for loop statement. How about for I equals 0 while I is less than 10 with a step of 1, put char d of I. Oh, let's do I plus I've been looking into some ASCII art recently, as you can tell. Okay, let's start with 0. So let's add 48 to this. See if this works. Oh, semicolon. Unknown function referenced. So it turns out that it was actually a stupid mistake that I made. In order to get the put char d function, I have to use the extern statement first. So I tested this and it does work. So I'm gonna put extern put char d. So now I have the ability to do put char d 48, and then that is going to evaluate to 0 if I do put char d 49. That's gonna print out 1. This one, and then it says evaluated to 0. Yeah, the function evaluated to 0, but it print out a 1. So now we can do a for loop like this. So for I is for I is 0 while it's less than 10 in the step of 1, we'll do put char d I plus 48, and then it prints from 0 to 9. So that proves that our for loop construct works. Okay, So I'm gonna stop this one here, and I'll see you next time. And next time we're actually gonna go tackle chapter 6. See you then.